Okay, does that work? Yes, yeah, sounds better. Thank you. So yeah, so my name is Mael Guennou from Luxembourg. I'm not a PhD and I'm not a postdoc, meaning you can relax and you don't have to worry about how good this presentation is. Yes, this one, please. Yeah. Right. So yeah, I'm going to talk today about the softening of polar phonon modes in this ferroelastic bismuth vanadate. So going a bit away from our classical perovskites. So this has been done, of course, in collaboration with many people. So at this stage, I don't need to go too much into anti-ferroelectrics. The motivation for this work was really that one. So I took this illustration before for another talk, but I think it matches the golden vibe, this kind of design for the image. I liked it. So we want new anti-ferroelectric materials in general. And why do we want that? Well, because there are not so many anti-ferroelectric crystals in the sense of crystals that you can really switch, okay? So antipolar is kind of trivial, but switching is very often the difficult part. So this is one thing, and in particular, what's particularly, say, unsatisfying is that this lead zirconate that we have heard is like super complex. The transition mechanisms involve like several order parameters, and also we've recently learned that the ground state might not even be anti-ferroelectric at all, but rather ferro or ferroelectric, if you wish, or in any case polar. This has been said already, but just to show it again, this is extracted from Hugo's paper here, where they show that the ground state might rather be this bigger unit cell here on the right, rather than the classical up-down-down arrangement that we know from the beginning. So we're trying to look for new types of crystals in new structures and not necessarily perovskites. So what makes us optimistic about the possibility to find such crystals is the following. So here I just took the three typical experimental signatures that we associate to anti-ferroelectricity for lead zirconate, and this goes back to Chirane's paper already in 1951. And of course, this double loop is the main one, but there's also this dielectric anomaly at the phase transition that we have, and there's this antipolar ion displacements that we also want to have. Now, the thing is, the double loop is rare. They say we don't have that many, but the two others, they are really extremely frequent. So those antipolar displacements, you find them, doesn't work? I think it might have. Oh, sorry. It's just sliding. I want to hear what you're saying. Yeah, or this. You might want to turn the volume a bit down now, or I have to. It's good? Okay. Yeah, so I was saying there's two other experimental signatures, like this dielectric anomaly and the antipolar cation or ion displacements. You find them virtually everywhere in any kind of phase transition, in fact. So there's no reason to think that there are not many more anti-ferroelectric crystals over there. And this is the main motivation. So what we're looking for is a crystal with a phase transition between two non-polar phases and a polar phase that's nearby, and also with an easy way to switch between the two. So what our dear theory colleagues do is to compute the phonon dispersions, typically try to look for structural immutability. This is an example taken from also a paper where also Hugo and Jorge were involved on the quantizide, and they can also compute switching path. Now, I'm an experimentalist. I can't really do that. Of course, I can take all the crystals around and apply electric fields until we burn the lab down. But instead, we can also try to look for indications that the polar phase is stable. And the best way to do it is to look at the dielectric constant, of course, in this dielectric anomaly, which here is shown in the example of the squaric acid, which happens to be a very nice model of anti-ferroelectric organic crystal. And look also in stabilities in the polar phonon modes, which also reflect a tendency toward ferroelectricity. So this work has already been kind of successful recently. We got attention to this particular crystal. It's not the main story for today, but I want to give you the main message from this past study. So this crystal is called francesite. There's a structure that's kind of complicated, but the phase transition itself is extremely simple. So it's here depicted at the bottom. And you see that mostly it's this kind of green small chlorine atom being displaced in along one line, so really one dimension, in an up-down fashion. So this was the phase transition. And so we studied this phase transition in a bit more detail. And this is really the final, say the main final message from this story. Here we are following the lattice dynamics, so the phonon modes, and there's two phonon modes we're interested in, right? There is the one that would lead to a polyphase here on the top, and which you see in infrared spectroscopy. And there is the one that corresponds to the anti-parallel displacements of the same cations, which we have to follow either by Raman spectroscopy below TC or by inelastic neutronal X-ray above TC. So when you put all those techniques together, you get this beautiful scenario, beautiful behavior for this simple transition, where above TC, you see that those two modes, polar and antipolar, they really go down together, right? So there is a tendency towards a polar or a ferroelectric transition, but then the antipolar instability is a bit ahead, reaches 0 first, and then everything goes up again and really advances. So this is the kind of nice picture that we are looking for in also other crystals. Also, what I want to mention here, experimentally, a nice indication that we can get from the experiments is the minimum phonon frequency that is reached around TC, which in this case happens to be 28 wave numbers. But for me, as an experimentalist, would be a measure of the energy required, or say the electric field required to bring this polyphase into real life. Okay, so this brings me now to the main compound for today, which is this bismuth vanadate. So the structure looks like this. It's called the scheelite. It's made of tetrahedra of vanadium oxide and bismuth. It has a phase transition that is from tetragonal to monoclinic. It is a proper ferroelastic, and the transition temperature is 525 K approximately. So it's already been studied in many details as early as the 70s and 80s. And more recently, it's also got attention because it has a nice band gap that makes it suitable for water splitting and similar applications. So what we knew from the literature already from this crystal is a number of things. So first, we were attracted to it by some kind of inventory that we did some years ago with Guennou. And we came to the conclusion that it should be, in principle, anti-ferroelectric. There's nothing against it. In terms of polar displacements, what happens at the transition looks like this. So the picture is a bit old, but hopefully you can still see the nice motion up and down of the bismuth and also the tetrahedra. The dielectric anomaly also somehow was known for some time, already back in the 70s. So in principle, we have a very good starting point, right? Now, the reason that makes it interesting in comparison to all those compounds in the list or any other is that it's a proper ferroelastic transition, meaning the transition is at gamma. It doesn't come with a doubling of the unit cell. So thinking of this as a potential anti-ferroelectric means that we would have anti-ferroelectricity without cell doubling, which is kind of original. By the way, Pierre Toledano continued on this symmetry analysis and also proposed that, in fact, all proper ferroelastic could be anti-ferroelectric in this way. So as I said, the transition has been studied already back in the 80s and 90s, so there's a lot known about the lattice dynamics. In particular, it's known that it has a soft mode, a soft Raman mode. This was the first observation. So with a soft mode that goes down, but not quite to 0. Then later, really a key point was the observation of the soft acoustic mode by Brillouin spectroscopy. So this was also a major step into the interpretation of this phase transition. And also, more recently, I mean, all the Raman modes have been measured. So this is fine, except that nobody had really looked into the polar modes before. So this is what we did. Long story short here, because this is really a classical exercise that you can do to check how many polar modes you expect in the structure and how they should behave. Here, I'm just going to concentrate on this red square here, where you can see that essentially for those modes polarized along the z-axis, which is the one that I'm interested in, there's 7 active modes in the low symmetry phase, and in the high symmetry phase, 3 of those modes become silent. So something very simple. This is what the infrared reflectivity spectra look like at 10K. It's very low. Again, long story short, everything works remarkably well. You find the 7 modes that you expect to see. And you can quite easily associate them to all the vibrational patterns based on calculations or even intuition, I would say. So when you go now and study this as a function of temperature, this is what it looks like here, across the phase transition between room temperature and about 600 K. So first thing I want to point out is how beautifully we see the phase transition here by these three modes that you can clearly see below TC and then vanish, right, when you reach the high symmetry phase. So this is also nicely consistent with the most mode assignment that we have. Now, what we're more interested in is the lowest polar mode, which is that one, okay, which I just magnify here a little bit. So you do also see a trend towards softening, right? That's even visible on the bare reflectivity spectrum. And when you do your fitting with the classical Lorentz harmonic oscillators, you do find a phonon frequency square that decreases and that reaches a minimum at TC. So all far so good. So the last thing, yes, sorry, just before that. So the frequency here, 72 wave numbers, significantly higher than the numbers I had for Franciside before. So we also remeasured the dielectric constant, so low frequency. So here you immediately see one of the issues that we are going to have with these crystals, namely that we do have an imaginary part of dielectric losses that do increase like crazy as soon as you get over, say, like 400, 450K. So this is going to make the measurement difficult. And this also explains that the shape, the exact shape of the dielectric anomaly is a bit difficult to capture for this measurement, but the presence and the principle of the dielectric anomaly is also very clear. What you can do to finish is to match those two together and compute the dielectric constant from the polar phonon mode frequency. And what you do find is something that's not perfect, but that tells you mostly that the value of this low frequency dielectric constant is dominated by the contribution of one single phonon mode that happens to be those bismuth with a polar displacement along the z direction. Okay? So this is pretty much it so far. I think this brings me to my take-home message on this particular crystal. So first thing, well, we have all the polar modes and it works well. Not particularly difficult, but it hadn't been done. We do have a pronounced softening of this lowest node at the transition, so this is also very good. Dielectric permittivity is controlled by this phonon mode. Frequency reaches 72 wave numbers at TC. So then if we now get to serious business and try to switch this thing, so objectively, I think it's difficult to expect that we can switch it close to the transition because the dielectric losses are going to probably be too high. But then there would be also strategies to chemically engineer this thing to bring the transition temperature a bit lower down and improve this issue. Last thing, first principle calculations in progress. So here I just want to anticipate on the first question that probably would be coming, right? Whether we have looked into this from a first principle point of view. Answer is yes. But answer is also that it happens to be a very tricky case from the point of view of DFT that really struggles to capture the ferroelastic ground state of this mid-vanadate. So starting from it, it's difficult to have a, say, reliable views on the structural instabilities and validate also a power instability from first principle. So this is ongoing work. We are collaborating with some theorists in Rennes for that purpose, and hopefully we should be able to say something soon. So with this, thank you for your attention, and of course I welcome any questions.
For telling us about explaining new compound, I think Ron has a question.
So I just maybe you said this, but vanadium then has a charge of 5?
Yeah, it's non-magnetic.
And is there any experiment that shows that that's really what it is?
Sorry,
is there any kind of spectroscopy that really shows that vanadium 5+?
I mean, there's a lot going on right now about optical properties in general. I can't say right now exactly, but yes, I mean, people have been looking into that very much.
Yeah, I think that was going to be my question. I was doing some quick valence counting too, and so I mean, of course, business also means some, multiple, whether, is that the origin of the difficulty in the first principles calculations of the
Well, on first,
titanium is not only such a high valence state, or
I can't really say at the level of first principle, although my understanding is that this 5+ for vanadium is kind of the easiest, right? Because I mean, there's no magnetism involved, so it makes everything simple. But it is a critical issue, I think, from an experimental point of view, because it certainly plays a role in all the leakage and all the difficulties to apply electric fields. So yes. By the way, this is a call to electronic rollers among us, if you want to give it a try. This is single crystal data, by the way, I haven't said that. Thin films exist. There are a couple of papers, but they can be made, so that could be also an option.
From the University of Minnesota. Thank you for the nice talk. You already did set the first question to the first case, so I will go ahead with that and ask why do you think the first principles calculations is actually failing here? Because I mean, I think many use probably on the field because in that technical coordination, it should be relatively stable at the final constraints. So is it the business doing something weird here? And the related question would be, do you know what's the, if this is gel contains their electric, or there's a soft model, do you know what's the driving force of that instability? Is it all pure business? Or is there something going on to the securities? I don't know.
So on your first question, I will just forward it to my theory colleagues, if you don't mind, because I really don't know. I mean, I can only say that when you try to compute the monoclinic phase, the actual ground state, it relaxes back to the tetragonal. And so now, why exactly this is the case, I really can't tell, but our colleagues have been giving thought of that. And they have been, the calculations they've been running is by doing different flavors of DFT and including different types of interactions and everything. So we're not there yet. We're not quite there yet, so I can't really say which interaction would be more important, but yeah, it's going on and it's kind of a longer work than expected. On your second question, well, that goes a bit with that, because if you ask me as an experimentalist, I tend to think that, you know, bismuth lone pair is what can provide the drive for color stability, but in this particular case, it might be more complicated.
Okay, Luxembourg. So thank you, Mael, for putting me on the spot, but I think I can say things over here. So DFT says no doubt it's vanadium 5+, bismuth 3+. So I'm very happy with that. The problem with DFT is that the high temperature phase appears as perfectly stable. This is my answer. We know for a while that hybrids use hybrid potentials according to this point. So and what the collaborators have been trying to do is to find more insight and a cheaper way to handle this. Probably has to do with the hybridization between physicals and oxygen orbitals and how you control that kind of bond, which probably indicates that this is the main driving force for the stability. So you know, that's what we know. But with hybrids, we can handle it. But DFT per se in the event was
yeah, absolutely. I would just add that with hybrid, you can stabilize the monoclinic phase, but when you look into the details, the structure is actually not that good as compared to our usual standards. In terms of monoclinic angles and everything, it's not great.
This is something from the University of Nebraska, Lincoln. Just for the follow-up question about the valence, I'm curious, in principle, we can do some fitting in the substance ball, get from, let's say, LTO splitting, some idea about the ball electric charge of the fission in the meeting. Can you comment a little bit on that?
Well, I can certainly comment that the fits work beautifully. So in the end, we have all the, we have the LTO splittings and we have all those things. But this is what we are trying to do now. So now that we have that, we are comparing with all the calculations produced by our colleagues and check what matches better. with this idea that those polar phonon frequencies are probably a very good indicator of the accuracy of the calculations. So that's, work in progress there.
All right, thank you, Mael, for your talk and for this great discussion. Thanks for leaving the time to take the clarity. All right, so now we're going to take down the chair. Mario, when you're ready to jump up and entertain you while we take the next talk. Okay, so I'm chairing this set of two Ferroelectrics with the food and lunch. Well, free lunch, but not like I said. First, let's see. 3 minutes. 5 minutes.